Today we're going to talk a little bit more about definite integrals, but first some notation. This symbol, read the integral of f of x dx, is the general antiderivative of f of x. So before, we would write little f of x was this, big F of x was that. Now we're going to write the same thing using this notation. So antiderivative of cosine of x is sine x plus c, and we will write it this way as integral cosine x dx equals sine x plus c. And this integral is called an indefinite integral. Notice that unlike the definite integral, when you integrate a function of x, you get a function of x. Where with a definite integral, if you integrate a function of x between two limits, you get a constant. Some more notation. In the fundamental theorem, we have a right-hand side that looks like f of b minus f of a. And to abbreviate that, we're going to write capital F of x evaluated between a and b. And that's how we'll read that. And it makes life easier in terms of evaluating definite integrals. So for example, definite integral from 0 to pi of sine x dx, well, we know that minus cosine x is an antiderivative, so it's minus cosine x evaluated between 0 and pi, which is just minus cosine pi, the top limit, minus cosine 0, the bottom limit, which is your f of b minus f of a. And when you do that, the cosine of pi is minus 1, the cosine of 0 is 1, so you get minus minus 1 minus minus 1, which is 2. Another example, definite integral from 1 to 4 of x plus 1 over the square root of x. Now to do this, it makes sense to actually carry out this division. Square root of x is x to the 1/2. X to the 1/2 divided into x gives us an x to the 1/2. And x to the 1/2 dividing 1 gives us x to the minus 1/2. And now these are powers. We know how to evaluate this using the power rule. It is x to the 3/2 over 3/2 plus x to the 1/2 over 1/2 evaluated between 1 and 4. And we then do a little simplification. Dividing by 3/2 is the same as multiplying by 2/3. Dividing by 1/2 is the same as multiplying by 2. We evaluate this between 1 and 4. And we get 2/3 4 to the 3/2 plus 2 4 to the 1/2 minus 2/3 plus 2. 4 to the 3/2 is 2 cubed or 8. 4 to the 1/2 is 2. So we end up with 16/3 plus 4 minus 2/3 plus 2. And when you do the algebra, you get 20/3. Now let's look at the following integral, the integral from 0 to 2 of the absolute value of 1 minus x squared. Now a problem we've got here is that we don't know how to take the antiderivative of an absolute value. So what we have to look at here is what's happening on the interval 0 to 2. And between 0 and 1, 1 minus x squared is positive. But between 1 and 2, 1 minus x squared is negative. The absolute value will, in fact, there give us x squared minus 1. Okay, so the absolute value of 1 minus x squared is 1 minus x squared when x is between 0 and 1, and it's x squared minus 1 when 1 is less than or equal to x is less than 2. And if we look at a graph, we can see that's exactly what's happened here. Here's the y equals 1 minus x squared, which would dip below the axis. The absolute value gives you the negative of it, and you get y equals x squared minus 1. Now what this means is this integral from 0 to 2 is going to be broken up into two pieces, between 0 to 1 and 1 to 2. And between 0 and 1, we use 1 minus x squared. Between 1 and 2, we use x squared minus 1. And we just go ahead and do that. Antiderivative of 1 is x. Antiderivative of x squared is x cubed over 3. So we get an x minus x cubed over 3 between 0 and 1. And we get x cubed over 3 minus x between 1 and 2. Now we just go ahead and evaluate each of the integrals. So x minus x cubed over 3 between 0 and 1 gives us a 1 minus 1/3 minus 0. And x cubed over 3 minus x between 2 and 1 gives us an 8/3 minus 2 minus 1/3 minus 1. When we do this, we get a 2/3 here. We get a 2/3 here. We get minus minus 2/3 or 2/3 here. 2/3 plus 2/3 plus 2/3 is 2. And that is the value of this integral. Next, we want to talk a little bit about the so-called net change theorem. And what it says, if you have a function that's differentiable, then the net change in the value of f of x between x of a and x of b is f of b minus f of a, which is sort of definitional, but because of the fundamental theorem, that's just the integral from a to b of f prime of x dx. So what that's saying now is that if you want to find out how much a function changes between 2 points, integrate its derivative between those same 2 points. So in application, if s of t is the position of an object, then the net displacement of the object between t equals a and t equals b is going to be s of b minus s of a, which according to the net change theorem is just going to be the integral from a to b of s prime of t dt. And of course, the derivative of position is velocity. So if v of t is 3 minus t, then the net displacement between t equals 0 and t equals 4 is given by the integral from 0 to 4 of 3 minus t dt, which is just 3t minus t squared over 2 between 0 and 4. And we put in a 4 here. We get a 12 minus 16 halves at the top. We're getting 0 minus 0 at the bottom. So 12 minus 8, or 4, is the net displacement. And what this means is that at t equals 4, the object is 4 units to the right of where it started from at t equals 0. Now, a little bit of a warning. This is not the total distance the object traveled between t equals 0 and t equals 4, because it may have gone backwards and forwards. And to account for that, we're going to have to look more carefully at 3 minus t, and we can see that 3 minus t is negative when t is less than 3. This definite integral gives the signed area, this counted as positive, this counted as negative. To get this to actually be the total distance traveled, this pink region needs to count as positive, and we're going to have to take the absolute value. Okay, so the integral from 0 to 4 of absolute v of t, which will now count this as positive, is going to be the integral from 0 to 3 of 3 minus t, plus the integral from 3 to 4 of the negative of this, which is t minus 3. And we just go ahead and do that. And the antiderivative of 3 minus t is 3t minus t squared over 2 between 0 and 3. And then we've got a t squared over 2 minus 3t between 3 and 4. Just put some numbers in. At 0, you're getting 0. At 3, you're getting 9 minus 9 halves. At 4, you're getting 16 over 2 minus 12. And at 3, you're getting 9 halves minus 9. You go ahead and do the algebra, and you end up with the total distance traveled, 5, which you'll notice is different than the net displacement, which was 4.